Hello, welcome to our lab presentation on the results from the hardness data testing by Mario Russo, Jeet Jamawala, and Sohail Kazi.
The purpose of this lab is to compare the hardness values of different metal samples, and each metal sample will vary in material as well as the finishing treatment. Some may be air treated, some may be oil treated, some may be untreated. Then we will analyze the calculated hardness values of these material samples, and then we will also compare the derived values between the Rockwell test and the Burnell test. So for this experiment, the samples we will be using is 1018 steel untreated, air treated, as well as oil treated. And then 1045 steel untreated, and we'll be using aluminum and brass. And the machines we'll be using to test the hardness of these materials is the Rockwell hardness tester, as well as the Burnell hardness tester. And we'll be using the vernier calipers to calculate some measurements. As far as the process of this experiment, we will start by preparing the samples. Whichever samples need to be air treated, we will air treat them. Whichever ones need to be oil treated, they will be oil treated. We will then start by calibrating the Rockwell hardness tester and run each sample through the Rockwell test a total of 3 times each. And then we will run the aluminum sample through the Burnell test. And Mario will kind of go in depth about how this experiment was conducted.
So after performing the processes that Sohail just described, we collected this raw data, everything just thrown into one graph as we did it. Here it's more cultivated, a little bit more organized. This is all the Rockwell testing, where you can see the untreated and treated steel samples, the aluminum and the brass, everything that was tested in the Rockwell test. You can see the comparative rankings between all the samples that were tested by Rockwell, which we'll get into later, what was stronger than the others. Here we have the data simply from the one aluminum test using the Brinell tester with the calculated hardness, average, which was average, and then used to find the yield strength and compared to a text value of 279 megapascals. And the indentation depth was also calculated by using the known diameter of the ball and the known diameter of the indentation it made. And if we assume that the ball was essentially just the radius sticking down or half the diameter, then using the same ratios of the diameters of the indentation and the indenter itself, we could simply use geometry to calculate how deep the indentation was actually made. Now, between the individual samples, as far as Rockwell testing goes, the strongest one that was tested was the untreated 1018 steel, followed by brass and the untreated 1045 steel. The weakest metal that was measured by Rockwell was aluminum, which was expected because aluminum is known as a soft metal. But what was expected was that the heat-treated steels were supposed to be harder than the untreated steels, which is not shown in our data. They tested to be softer than the untreated steels. This is likely because when we heat treated the steels, cooled them either by not so much by air, but more so, especially with the oil quenched steel, it built up this carbon buildup along the steel sample, which would only be removed. It was flaky. It would be removed when first performing the hardness testing. So it really started to shatter when you performed a hardness test, and then you could sort of sand it, but still not very well to remove it. So the data we collected is actually the hardness of puncturing that first flaky shell instead of the actual hardness of the steel itself. We would have removed all of the buildup individually and then properly tested it. However, there wasn't enough time in the lab to actually fully clean the samples and then retest them. So the data we have is what we have, and it's sadly inaccurate.
So to tie it all together, the purpose of this lab was to find the hardness of different materials using the Rockwell and Brinell tests, and our results were really, really good. Besides the untreated and the heated steel, because usually the heated steel is supposed to be more harder than the untreated one, and the findings just like did not add up to that. Yeah, and as Mario said, like we think it's because the flakes of the steel, we were not able to get the accurate measure. And usually the untreated, the data we got was the untreated steel was 93.7 on the hardness scale, and the heated one was 87.3. So usually it should be the opposite, or maybe the heated one should have been more than 93.7. And for future work recommendations, maybe getting like a fresh calibration block, or maybe a newer one with less indents, because the one we had so many ones that we had to just make sure that like we're getting the right spot, and it was just too crowded. And the TA told us we cannot like go to the edges, because then that would just mess up the calibration. So a better calibration block would be great. And then more accurate measurement for the indentation. We just used calipers, which was fine, but maybe if there's another way to I don't know, just like able to find a better like diameter for that, because I just eyeballed it. Like we saw the indentation, we used the calipers, we eyeballed it, and we just got the data. But maybe if there's a better way, then that would give us way more accurate results.
I would like to add that while the data showed that the heat treated steels were softer than the untreated steels, we still got the right correlation that the oil quenched steels were still harder than the air treated steels, which is what we expected, and that still showed itself in the data. And these are our references. The first one is just where we derived the literature value of the aluminum yield strength from the website MatWeb, and the other two are the references from the lab manual. Thank you. This has been our presentation.